recording officially. So welcome back to the show. I have the course webpage up to remind myself what all I wanted to talk about with you all today. Y'all, sorry, I slipped. I said you all again. Still working on it. So thank you everyone for getting both of your activities done. Everyone did everything. That hardly ever happens, so good work. So I have a formative assessment number 3, homework 2. I wanted to go over the problems to the example 2 challenge, as well as the items on my list of review topics that you all answered for the last question. So with respect to formative assessment number 3, a few of you reached out to me to let me know that you could actually see your scores. That was as intended, because originally in my plan, I like to have formative assessment, then homework, then formative assessment, then homework, so that you have a chance to benefit from the discussion of the assessment. However, because of snow and ice, which no one saw coming, including me, we got behind on the schedule. So instead, I decided to let the answers be visible right away. So let me give you the backstory, and then I'm going to take an informal poll, okay? In my previous courses, the formative assessments were all open-ended essay types. Like I would just ask a question and I wanted to see what people were coming up with. I would collect the answers and we'd talk about it during class. Feedback that I had gotten about that process on our course evaluations said that folks felt like they couldn't ask questions because they didn't have a sense as to how the rest of the class was doing. Like they felt like they were the only one who didn't understand something, which, you know, is never going to be true, but I can see how one would feel like that. So as a solution to that problem, I started moving the formative assessments into a multiple choice format so that then there was a correct answer, at least as I had intended it, and then folks could see how many people picked some of the distractors instead. So that's one option. But then that requires you to have delayed feedback and you don't get a chance to directly edit your answers for credit, which can be discouraging. So then this other version is, I don't care, you can see the answers and you can correct them and you can get 100% if that's what you want to do. So of the folks who are here, do you have a preference as to how I can move forward with these? Do you like seeing your feedback right away? Or do you prefer to just take it once and then we talk about it during class and then you can see how many other folks may have selected the same distractor as you? Any thoughts on that?
I personally like seeing my feedback right away.
Okay. So 1 vote for right away, 2 votes, 3. I'm sensing a trend already here. I have the wrong camera on, that's why it looks like this. Okay, there, now you can see the room and me. We'll take a poll on that. Which view do you like better? Direct camera or owl camera? This is more of a Zoomer feedback. Y'all are stuck with me in front of you, sorry. That's how it works.
Direct I think the direct is fine.
Direct is fine. Okay, there's 1 vote. 2 votes. Direct, you got it. Half dozen or the other. That's one of my favorite sayings. Just don't say that in Europe when you're teaching to students. They're like, what are you talking about? I also started a lecture in Germany once with, if I had a nickel for every time a student did, and they're like, yeah, I don't know what a nickel is, but thanks for the story. So, all right, so we're voting on direct, and so far immediate feedback is better. We like that as an option. So then you're losing the ability to see that you're not the only one who didn't get it perfect on the first try. That's the compromise. If you're okay with that, then I can give you immediate feedback. That's no problem. I also learned that if I make the open-ended question worth 0 points, you get to see your feedback. But if the open-ended question is worth any points, you don't. So if I do this in the future, I will make sure to set it for 0 points. So everybody earned 2.25 points for doing the activity and then up to so much more afterwards. But I still think it may be useful to go over the answers to that. So let me get the screen share going for the Zoomers. No meeting, hide controls, and then we're in business. Okay. So example empty model. Empty meaning no predictors, so you have nothing to go on. So the idea that I wanted you to have on this, you should be able to see your score for FA2. Yes, everybody should be able to. If you cannot, then I'll have to check on that over break. Because that one I had fixed during the previous class. If you resubmitted though, and I haven't regraded it, it might not show it because of the last one, but you should be able to see it in grades. I can work on that over break. Okay, so for an empty model, the key idea is that it's starting off with your best guess for everyone is the mean, and the amount of variability in these E's out here is all the variability in negative mood. And so these questions I realize are potentially confusing in that you're selecting the wrong answer. And everything I know about cognitive psychology says don't ask it that way. However, the reason that I'm doing it is because I want you to start to recognize equivalent ways of saying the same thing, because we don't all express it the same way. Disciplines have their own way of talking about things. And so I'm trying to give you examples of trying to recognize when something is the same versus when it's the oddball. So you can say this a bunch of different ways with respect to if the variability of these E's here, so E, remember, is how far wrong the model is in predicting your outcome. So in this case, it's all the difference between each person's negative mood score and beta 0, which is the fixed intercept, which was the sample mean in this case. So 100 represents all the variability in negative mood. That is correct, because there's nothing else to explain it at this point. And if you have the formula for variance, you're literally deviating each score from the mean, which would be all that beta 0 is here. So it is the same thing. 10 represents the average distance of any person's negative mood from the mean. So that is talking about the standard deviation. So 100 would be variance, the square root would be 10. So that's also the same thing. And 100 represents the remaining variability after being predicted by the model fixed effects. That is also true. But in this case, the remaining variability is all the variability because all we have is a fixed intercept. So all three of those things mean the same thing. The oddball then, the expected inconsistency of the mean across repeated samples, what is that instead? One of these things is not like the other? Yeah, that's the standard error. So expected behavior across repeated samples is a standard error of some kind. So any thoughts or questions on that? Good so far? All right. So then, if the empty model predicting negative mood returns a standard error for beta 0 of 0.5, which is correct. Now this, in that case, this is the expected fluctuation of that mean across repeated samples. It's how far off from the population mean it would be on average. So this one down here, the average difference of any person's negative mood from the mean, that's standard deviation instead. And several folks asked for a review on that topic, so we will talk about that as well. 0.5 is the amount of variability in negative mood across persons in that sample, that's variance. And then this one is just a bad distractor, I would say. Fortunately, no one fell for it. Sleepover. So, spoiler alert, when children have sleepovers, there's very little sleeping. That's why I don't let my kid do that. But I remember going to them as a child, and the next day my parents suffered on my behalf. Let's just put it that way. So my equation here is negative mood starts off at 60 as the fixed intercept, and the slope for the effect of a sleepover is 8. And so note how sleepover is coded. 0 is no sleepover, 1 is sleepover. So that is often, when you see variable names, like in result sections and things, they often name it for what the one group means. So sleepover means, yes, I had one. So in this case, the fixed intercept is always the expected outcome when your predictors are 0. In this context, that means for children who didn't have a sleepover the night before, their predicted negative mood in that group is 60. For children who did, the negative mood increases by 8. So the 60 is sort of like the model reference, the "you are here" sign. The 8 then is the effect of having a sleepover relative to not having one. So what would happen, do you think, if I recoded this so that the 0 group had a sleepover and the 1 group did not? How do you think that might change?
It would decrease, right?
By how much?
By 8?
Yeah. So then what would the intercept be? Because we're changing who the reference is. If the reference was the sleepover people, new intercept be if we switched what 0 and 1 meant? I'll make it multiple choice. 52 or 68? Yeah, so if you think about what is the predicted outcome for a child who had a sleepover? 60 plus 8. So then if that is your new 0 point, the intercept would become 68. What would happen to the slope? It would have to go negative. So it's like the opposite, but it's the same information just given to you from a different perspective. From the "you are here" sign is a child with a sleepover, then it would be 68 minus 8. If the reference point is a child without a sleepover, then it is what it is here. And the rest of these then mixed up the sign and or who the zeros and ones were. All right, so what if sleep were continuous? So if we have a residual variance of 80, now at this point, E and negative mood are different things. This is the point at which we start talking about the idea of variance left over as residual variance, because sleep explains part of the variability in negative mood via its slope beta 1 here. So we have to figure out then how much is left. So which of these is incorrect? The one that says E and negative mood are the same thing. That 80 is the overall amount of variability. That's incorrect because we have some of it explained by sleep. So the rest of these then are 3 different ways of saying the same thing. 80 is the variance of these E's specifically. 80 is the amount of variability that is unrelated to sleep. So the idea of leftover and residual, those are synonyms that you can use. And 80 is the amount of variability not accounted for by the model. That's another way of saying the same thing. So I will use the term leftover and residual interchangeably because I think leftover has a more accessible definition. But if you're writing about it, it's residual variance, not leftover variance. There's a lot of things I say when I'm teaching that I would never put in a paper. Even the non-swear words. Leftover is not a technical term, but it's useful. All right, questions so far? Feeling okay? Can I do a thumb check? Okay, concepts are okay. R code, not so much, I'm guessing. We'll have a little more variability in the thumbs at that stage. All right, moving along then. If the same model predicting negative mood from usual hours of sleep returns this solution, which is correct? So 110 would be the expected value for someone who never usually sleeps, because that's what a 0 value of sleep would mean in this case. So this is a situation in which we would want to center the predictor so that the intercept represents the expected outcome for a person who's actually in our sample. The other distractors, 110 is wrong. Now, it could be perceived as wrong because the pretend scale of this variable is from 0 to 100. It's not wrong, though. It's just weird. It's a logical consequence of the line that keeps going no matter where you are on it. It's a linear slope, so it continues regardless. If you want to make sure that your linear slope shuts off to obey the boundaries of a variable, you need a different kind of model. That's a generalized linear model. So 110 is not how negative mood is predicted to change per hour of sleep. That would be a slope, and it can't be the mean either because it's conditional on some value of sleep. So another way of thinking about an intercept is that it's a conditional mean. It's conditional on the particular kind of value that your predictor has or multiple predictors have as we get to more complicated models. So then what would happen if sleep were centered at 8 hours? We can do the same thing as in the last formative assessment. Do the math to plug in 8 here. So 110 minus 5 times 8 gives us the solution that 110 would become 70. Would the slope change? Nope, and it shouldn't. You should not be able to adjust the size of the relationship between variables just by changing where 0 is. In linear transformations, people stay equally spread apart. In different kinds of nonlinear transformations, you will change the relationship. So if you took the log, for instance, or the square root, or something like that, then that differentially squishes people, and that will change the relationship as a consequence. We will see examples of that in Unit 3. So correct interpretation of beta 1 slope equals -5. That is the amount that negative mood is per hour in this case. I think that one is fairly straightforward. Here's one that I want to go over a little bit more in detail, because I had several folks mention in their request for review topics how to understand the tables in R. So figuring out how the values connect to each other can be tricky at first, and so I want to focus on that. So for negative mood as the outcome and sleep as the predictor, if I have an estimate of the slope of -5, and if its standard error is 2. So -5 is the answer based on what value would make the e's collectively the smallest. Standard error tells us how far off from the population slope we are expected to be on average in any one sample. It's an index of wiggliness or inconsistency. So how do we get to t out of this? Division. So slope divided by standard error, and we have to keep the sign. So t is unsquared. So if your slope is negative, your t is negative. So negative 2.5 is correct. 2.5 drops the sign, and the other two get the order backwards in terms of what is divided by what. So we will walk through that in R as well. This one is a little trickier. Which of the following is wrong, incorrect? So what t's role is to locate a result on a null or expectedness distribution. So all of these three options are different ways of saying that. It relocates the slope on a standardized metric where you don't have to know what x and y are to know what the value of t means. So anything past about plus or minus 2 is usually an indication that it's unexpected if the true relationship were 0. So it is relocating a unit-specific slope on a unitless or standardized metric. It is a standardized way of expressing how far away from the null a sample statistic is, such as a slope. And more simply, it's a ratio of signal to noise. So if you can think about it from like that sort of perspective, then t being bigger, like it's twice as 2 would mean it's twice as big as what you would expect based on normal fluctuation. But it does not directly dictate whether a slope is significant or not. So I have a little activity that we'll walk through that helps to illustrate this point, I think. So any questions on that thus far? I see unmuting. That looks promising.
I guess I'm wondering what, and I don't know, maybe I like missed words that were surfaced. Like conceptually, what is signal and what is noise?
Signal means how far away from 0 a slope is. So like if there's no relationship between variables, the slope is flat, meaning that as you go up on x, it doesn't tell you anything about what's going to happen on y. And the noise is conveyed by the standard error, meaning like how wiggly would you expect the slope to be relative to the right answer on a normal basis?
Okay, that's helpful.
It may not be, but I get points for trying.
I hear people talk about signal and noise all of the time in a bunch of contexts, and I never know what they're talking about. So I guess I'll go in with this frame and when anyone that says that and see if that's actually how they're using it.
Yeah, like oftentimes in life, we are willing to accept some error to judgments, right? So like this morning, I took my parents back to the airport. They visited over the weekend from Omaha. And, Apple Maps told me it would take 53 minutes. Like that's an estimate. It actually took 57. So it's like, were they wrong? Or is it that's just an expected amount of error to the system of prediction based on traffic and weather and accidents and whatnot? So I don't know what the standard error is for Apple, but if I did, it would inform how early I left. It's like, what is the expected error? I want to make sure I beat that so my parents don't miss their flight. Does that help? We'll
I
keep working
think
on
so.
it.
Yeah, I think that's helpful.
Okay. I have more about tea in just a minute here, but we'll finish this one first. That way I can make sure I get to the rest of these here. So which of the following is not relevant in determining the critical values? So these are the goalposts, so to speak. So in football, you expect a kicker to make it through the goalpost, right? That's expected territory. You don't expect them to go on the outside. And that ends all of my knowledge of football. Thanks for playing. That's the end of my sports analogies. So what does affect where the goalposts are sample size. It's easier to get outside of them for bigger samples. The number of fixed effects, so these two things in particular, sample size minus the number of fixed effects, is what's going to be called denominator degrees of freedom, and that dictates the shape of T, basically how squatty it is. The lower the degrees of freedom, the squattier it is, and the more area is in the outside, so it becomes harder to declare it unexpected. Alpha level also dictates where the goalposts are, and whether it's a 1 or 2 tailed test dictates whether it's one goalpost or the other instead. So all of those things essentially set up the rules of the game for declaring something significant. But the slope itself should not be able to change the rules. Like, that's what happened after the fact, and you have to live with it. But the rest of this is somewhat under the control/decision of the researcher. But the slope itself, you can't control. Unless you're going to fake the data, and I would not recommend that. Incorrect. So I know this one's a little tedious, but drilling the idea that this is algorithmic to the point where I can write a program in SAS that builds your homework paragraphs, because this is literally the code that I write when I'm checking against your response. So alpha 0.05. If alpha is 0.05, that means setting one of the decisions and setting where the goalposts are, and the p-value is less than that, the result is non-significant. That's wrong. So good job, everybody. If the p-value is less than that, it is significant. If the p-value is greater than or equal to non-significant, so that's another one that folks get tripped up on. If the p-value is exactly 0.05, it is non-significant. It needs to be less than. If alpha is 0.01 and p is less than 0.01, it is significant. And then if it's 0.05 and the p-value is less than 0.01, it's significant, just by a more comfortable margin. Correlations. I'm sure that this went well for folks since you got this right last time, but just to make sure, the bigger the number, the bigger the relationship. The sign does not matter. The sign that being negative just means that if you are higher on X, you are lower on Y instead. And a negative T statistic would follow a negative slope, meaning that it is less than HO. So it would be a negative relationship rather than positive on that one. If a significant p-value for a fixed intercept is found, that just means the expected outcome is different than 0, and we usually do not care about that. So we can just disregard that part of the output. And a few folks wrote me emails that this question was trying to anticipate. If you get the residual variance for your model right in R, that is like a thumbprint for your analysis. That means you have the right information, you have the right outcome, and you have the right predictors. If you get anything regarding the fixed intercept wrong, meaning its estimate or its standard error, then you have the wrong definition for what 0 means for your predictors. That's what it has to mean. So that's a dead giveaway that something went awry with the centering. All right, and the answers that you wanted to go over. Let me pull those up. So I'm not going to show them in the interest of privacy, but I will summarize some of them briefly. I'm not sure if I know what I don't know. I think I'm feeling okay, but I don't know. That's a common thread. Does anyone else feel like this isn't English and I have to watch something or listen multiple times before it lands? Yes. See? The Zoomers are excited. So it is not just you. That is what I can personally guarantee. So I answered several questions yesterday from folks who were realizing what they didn't know, particularly with respect to R. So I did want to go over some of that stuff. Other topics folks mentioned: residual variance versus standard error, which ones are squared, how does standard deviation factor into that, and then questions about output. So in that, I thought it might be helpful to go through the challenge activity that I did at the end of class. A few people stuck around and worked on that. I just want to go over a few things that came up in answering questions over email. So I'm looking at R right now. This is lecture, actually, should be example 2. Apparently I did not change that as I had anticipated. There we go. All right, Zoomers, is this big enough for you? Do I need to make it bigger? It's okay? All right. So I have I have several syntax files open here. Let me just get rid of some of them. Actually, I'll need that one. So I have just syntax, and then the console is at the bottom in this case. So in terms of what you need to be able to analyze data in the future, and in particular to start practicing analyzing data in homework, there's one distinction that came up repeatedly in folks' questions. So this section of the code right here, where the comment on line 15 says check to see if packages are downloaded, install, if not, then load. All you have to do at this stage is run these commands. So you don't have to go download anything separately. You don't have to unzip anything separately. These are packages that are inside of R's architecture, and all you have to do is ask for them to be loaded into your current programming environment. So this is something that you don't have to go search for, any of this. They just work as intended. And I have notes here as to what each of these things is for, to remind myself why I initially downloaded it. If things go sideways and you want like a clean slate of your environment, you don't have to restart R. If you uncomment, this is line 37 here, if you uncomment this command and run it, it clears everything out for you. Your data, your functions, everything. So it's like you get a fresh slate, so to speak. More generally, any code that you want to hang on to, but that you don't want to have active or executed, you can put a comment in front of it just so that it stays as part of your record. So I heard from folks over email that like they felt like they've tried 10 different things and nothing's working. Well, my question would be, do you have a record you tried that didn't work? Because I would do that. Like rather than erasing it and starting over, I would put a comment and be like, this didn't work, this didn't work, this didn't work, because then it's like you can go back and see what you've tried, and process of elimination can hopefully make it a little more efficient. Or you can see patterns like, oh, this didn't work because, oh, this didn't work because. And so leaving notes to yourself is really helpful. Down here in the console, you can type things. Please don't. Like the future you does not want you to type things into the console, because once you type it, it's gone. And you don't have an example for future you of how to do the thing you just learned how to do. It is much better for future you and current you, I would say, to do your syntax up here and then run it so that it shows up down there. Because you'll find yourself needing to do the same kinds of tasks over and over again. And what I do is just pull up something that's similar to that in the past, start from there, and then copy it over and modify as needed. Question?
What's the difference between the using that broom to clear out your workspace and using that command clear workspace?
The broom is localized. So let me run something so that I have something down there to clear. Okay. Down here, the broom just removes like the visual output from the console. Whereas the other clear thing, let me see. Let me input, where's the data? Files? Nope. Environment. Where did it go? I moved the console over and now it's all like confused. Come on, where's my stuff? 1 second, I've lost it. Well, let me put it back. No, not you. This thing up here, again, this command not just clears the output, it clears all the data sets, all the objects, all the functions, like anything that you have loaded into the environment, it erases that. So it's like the broom like sweeps your floor, and this clear workspace like knocks down your house.
What if you use the broom that's in the environment and the broom down there?
That may do both. I have not broomed my environment before, to be honest with you. I usually do this one. My husband gave me this command, so I usually trust that he has reasons for why he does things a certain way that I'm not privy to and I don't need to know. But where is the... Now this is very odd. Like my normal environment thing is missing here. What am I missing? Where's the window? Yeah, it's like it rearranged all my windows and I can't find the environment section, but that's okay. We don't need to see it to know that it's working. I know, thank you. I'm not the only one who's crazy. Like, where's my environment? I just loaded data.
I have a quick question.
Yes.
Okay, so in the email, you wanted me to send you a copy of it's not the
Syntax?
script. Yes, syntax.
Yep. So the script, syntax, and code are all synonyms.
Okay.
Yes, this file. So occasionally, like the screenshot will show just the command that you ran, but I can't see like what's immediately before it that it's pulling information from. And so like if I can see the sequence of what you did, like if I can't troubleshoot immediately, then seeing the steps that came before it to see if that's where the issue is, that will be helpful.
Thank you.
Yes, yes. So my first pass in terms of answering questions is a screenshot. Second pass, if I can't figure it out from that, would be sending the full file so that I can look on that. All right, now I know why it's mad at me, but let me run the packages. So we get those. So it's loading things. It's like, why is my environment empty? I tried to input data. Let me see here. Let me run this again. Okay, so this much is what I gave you for your, there we go. Thank you. It's working now. For your starter syntax for your homework. So where you downloaded your data set, there's a starter syntax that basically has this sort of shell to it. Has the packages, has where you should paste in like the name of your data set, and paste in the working directory. Now this step right here, I got several questions about. The functions file that I built you. This is something that R doesn't do. This is something that you have to do. So in the same folder where the example 2 syntax is, that was for homework 2, you would need to get the file that is called edf9770_functions.r. That needs to be in the same folder as your data set and your syntax. So basically copying those two files manually over to the folder. You don't have to run it though, like you don't have to open it or do anything. Instead, when you just run this one line, this source command right here, it essentially takes that file, runs the whole thing, and then it puts the functions in here that are needed. So if you get an error message that says it can't find LM summary, this is why. It hasn't taken that external file and put it into its working environment yet. And every time I give you an example, I will put a functions file with it. If you are interested in learning more about programming, you can look in the functions file. I'll open it right now just to show you. All right. So this has 2 additional packages that this uses. It has all the arguments that are possible within this analysis. So for instance, LM summary defaults to a 95% confidence interval. You can change that to any other kind. It defaults to 3 significant digits in terms of after the decimal. It defaults to no effect sizes and no explanations, and it defaults to printing equals true. The rest of this is, and you can see it's very heavily commented because I don't trust myself to remember these things. It's just me rearranging output and then doing math to add things to it, such as effect size. So I didn't think you would want to see all of this code at the start of your homework files. I thought this would be very overwhelming and unhelpful. That's why I stuck it in a separate file. So you don't have to touch this. It should work for the problems that we are using. All you have to do is have it in the same folder as your data and your syntax file, and then just run this line to start it. Okay, does that make sense? Or are there questions I can help with?
When you say just run that line, I just have to run that one line?
This one line, so assuming you've run everything up to this point, I should
Yeah,
say.
well,
It's hierarchical. So this, just as a review, these packages are our packages. You don't have to re-download them. Like if you've already done that on your machine, it will just load them and it'll go faster. If you're working on a different computer than usual and you haven't downloaded them, this will do that. So this sort of sets up what you need for your workspace. This line 47, the set working directory, that tells it where to look for stuff. So if you were to just run this without that first, it'd be like, where do I find this file? Because there's no context in this one statement as to where that file is. The context is implicit that it's within this working directory. So if you don't run that first, then it won't work. Yeah, there's a reason the steps are like in the order they are, like they're not, they have to be this way, basically. Same thing here, like if I try to import my data before I tell it where the data are, that's not going to go well. It's the same thing. So I have imported the data, I have loaded the functions, and now the next thing here, I had a few questions about this text start. This command is optional. This command, what it does is take everything that's going to your console and it dumps it to a text file in that same folder where everything else is. So I believe in my starter syntax, I had commented it out because what can happen is that if you rerun things, like it's going to get mad at you because it's starting multiple times without ever ending. So if you get error messages related to this, then that means it's looking for the complementary ending code, which is always at the bottom, and that's this text stop command. So that's how you get it back onto like even ground. If you run the start multiple times, it's looking for the end, and then that way it closes the file and you can reopen it to write to it as needed. But you don't need to do that until you're like all the way through your troubleshooting and you have results you want to save. Like I would not save the process. I would only save the code in the process, if that makes sense. So I'm not going to execute this right now. Okay, other questions so far about how to get things into R or loaded? All right, then we went through this much in class, and I had put in challenge problems, so to speak. So I wanted to go through some of the results of that, and as a means of practicing what the tables mean, and also a little bit of troubleshooting. So I had started a new text file for this, just this little piece here, and I had posted this answer key and that one in the example2 zip folder. So the first question was write syntax to predict science from locus of control, in which 0.5 is the reference. I should have said for locus specifically. Let me add that for my future self. What do you conclude? So first step is to make a new variable in which you are subtracting the centering constant. So example 2 locus 05 is what I decided to call it because it's 05 here. Example 2 is the name of the data set. Locus is the name of the column. And I know that because, oops, I can look at the data set that way, or I can click it once and just get the names of everything. For shorter data sets, that's a perfectly reasonable way to do it. So the first step is that I need to make a variable. If you end up with the wrong answers and you've been messing around with these numbers, I would just rerun this and see if it works. There were a few folks that was the case. They just had to re-import their data and rerun it. It had somehow gotten off track versus different tries. So once you run this, you should see a new entry here that is locus 05, the number, the new variable that we just made. And that is the same variable, just with minus 0.5 as the operation that makes the new column. So then the question is, how does it predict science? So in my LM call, I'm naming this science underscore locus 05, meaning predicting science from locus of control. Formula equals science is the outcome. And then I got a couple questions on this. What's that character, folks? It's tiny. Yeah, squiggle is what I call it. I would also accept tilde.
That's the tilde, and you need your reading glasses to see that.
Yes, at least one person put a dash in instead, which again, visually looks very, very similar. But nope, R is like, what? No, how dare you? So the tilde is next to the 1. That's not one that folks use very often. And the reason that it has to be this way is that if you put a dash here, it's interpreting it as a minus sign. If you try to put an equal sign here, it gets confused because equals is how you tell it what the argument to the function is. You can't reuse it in a different way. So whoever wrote this command decided on tilde, and we're stuck with it for better or worse. All right, so then I'm asking for a summary, including effect sizes, and I'm going to add explanations to this. Explain, oops, no. No cap locks. What happens if I use cap locks by accident? Will it be okay? It will not be okay. It'll be like, how dare you? This is case and space sensitive. Even though I knew what you meant. I'm going to run all 3 of those things and make the output big. Okay. So first check, is everything green? Or not green, blue. Blue is good, red is bad. So even if you get numbers, get in the habit of looking at what happened ahead of that and generating the numbers just in case something went awry. It can happen. So there are 3 tables here that we've generated. Sums of squares, which I have only waved my hand at so far. That's coming in Unit 3 because we haven't needed it. The one number that I've asked you to pay attention to is right here. That is where your residual variance is. What the rest of these things mean will have context once we have more than one term in the model. But the names of the columns are explained right here with the explain equals true option. So some of these are familiar. Degrees of freedom, P, and potentially R square are things you may have seen before. Fixed effects. This is what people call the solution or the answers. And in the type of, how do I say this? The type of estimation we're doing, meaning process by which you find the answers, is called ordinary least squares. And what it does is figure out the values that collectively make the e's as small as possible in your sample. It turns out that you don't have to search for this. There's a matrix equation that does it. So this goes really fast and it's really reliable even for large data sets. So this isn't something that you have to worry about the solution not getting to the right place. In advanced methodology, you do have to worry about that. That's called model non-convergence, but that's never going to be a problem with these types of analyses. So the estimate column, that's what EST means as an abbreviation. This is the answer. This is our best guess as to what the intercept should be for somebody who has a value of 0.5 on the locus of control scale. Likewise, the value that is next to the predictor is its slope. So that would be what beta 1 was estimated to be using these data. That's the slope that collectively makes the e's around that slope as small as possible. So we would say that somebody who has a locus of control of negative 0.5, which is just shy of the average, has an expected science score of 53.66. And then what happens to it as your locus of control goes up? This can be a finger question. I mean, what? Up. Yep. So for every unit of locus, whatever that is, science goes up by 4.7. Is that a lot? Is that good? What's it relative to? So we go over to standard error. Here's the expected fluctuation of that slope. Only 0.5. So the fact that it's 4 tells me that, yeah, this is way further away from like the middle of 0 than would be expected just by random fluctuation from sample to sample. So if we take 4.7, divide by the standard error of 0.56, That gets us to our t value here. So t is a test statistic. Say that 5 times fast. That's why I call it t value. I can say that one easier. But more generally, it is a test statistic. So this is the signal to noise ratio. This is the location on a t distribution of your slope given these parameters. So said differently, this slope of 4.7 is over 8 standard errors away from 0. Way more than 2. So definitely positively unexpected. A slope this unexpected would happen less than 1 in 1,000. So definitely less than 0.05. So this is a p-value. These are confidence limits. So here's the lower one and the upper one that essentially describe the expected variability of the slope across samples. The technical definition is that this is the range in which the population slope would fall 95% of the time. I never say that. I never put it in papers. It's convoluted, but you can think of this as an expected wiggliness kind of personified. The fact that this does not overlap 0 coincides with the p-value being significant. So 0 is not within the range of expected fluctuation for this analysis, for this result. Okay, how are we doing? So folks who wanted to look at R, what do you want to know about R? I promise it doesn't hate just you. It hates all of us equally. R is an equal opportunity demotivator, as it were. Then the next one, if there's none. Okay, yes, I hear a hand. There we go. Where'd it go?
I was just wondering, it seems like we have to input individual data to find out like a list, whereas like when we used Jump last semester, I know it was different data, but it just gave us like a whole bunch of data at one time. I feel like I had to go back a lot and add different syntax to find each additional piece of information.
So when you mean data, do you mean like a data set or do you mean a piece of output?
Yeah, like interaction between I don't know if how to explain it. We had to like compare math and writing, and then we had to go back and do like, yeah, let's say math and science, and then you had to go back and do locus versus science instead of just having like multiple comparisons at once.
Oh, okay. Yes. Within most R functions that are designed for univariate analyses, meaning predicting one thing at a time, you do have to have it be, it's one command per analysis. So the exception would be something like a correlation matrix, where you can have multiple rows and multiple columns of variables at the same time, and you can get bivariate relationships. But when it comes to fitting a model, it's one outcome at a time. And so each separate model that you would want to examine is a new line of code. So if I just did this much, here, let me show you another common thing that folks sometimes get hung up on. I'm going to broom my output here, get rid of that. So if I just do this, what do you think will happen? Just that line. See, it ran. It's not mad. Where'd it go? It's over here. So science underscore locus 05 is an object over here. So it saves a whole bunch of information about your analysis, a whole bunch, but it doesn't print it. So the next piece of that then prints it. So this version actually takes multiple commands that you would have to write. Like there's a separate command for the sums of squares table. There's a command for the fixed effects. There's a command that would generate effect sizes. Like I'm trying to keep it so there's only one thing that you have to type that gets as much output as would be useful. If you want to see the alternative, look at this same type of course at Iowa. few rows back, I had a lot more code to it before I got better at stacking things together. So I am trying to help, but it is true that you only have one model at a time per line. So to get the actual answers, that's what this LM summary part does down here. And the fixed effect sizes, that was one I had a couple questions about as well. So let's see, I had lecture, let me find the slide for it. I'm going to open up lecture 2 since we're going to be back in that talking about power in a little bit. It's thinking about opening. There we go. Go over here. Yay, it stayed. Looking for one slide that has formulas on it. PowerPoint is feeling as sluggish as I am today. It's like, no, I'm not going to load. Just no. Come back later. Here we go. This one. This is slide 60. This is what I wanted. So you can take a t-test statistic and convert it into a couple different kinds of effect sizes. So an effect size is a generic unitless way of describing how related two variables are. So you don't need to know what X and Y specifically are. So the one effect size that we've seen so far is a correlation. It ranges from -1 to 1, regardless of what kind of variables you have. You know that a correlation of 0 means there's no relation, ranging all the way up to 1 as the strongest possible relation, or -1 as the strongest possible negative. D is one that is also used in a context in which you have a categorical predictor and you want to know how different two groups are. So D is part of a standardized mean difference family, and here is how you can compute D using the results of the t for that slope. It's 2t divided by the square root of denominator degrees of freedom. Well, rather than making you write R code that does that math, that's what my function does. It goes into this output table, borrows these t's essentially, grabs degrees of freedom from another piece of the output, and then appends D and these two other effect sizes onto this table. So the first part of the table is the same, estimate and p-value. That's just a repetition of this number and this number, because that's what people typically use for interpretation. Locus of control is the slope we're looking at here. So D is Cohen's D. Go away. There. Cohen's D. So this means that if these were groups, this is how far apart they would be. In this case, because they're not groups, D is not as useful. But we can also get a correlation type effect size, R, from the same information, T and denominator degrees of freedom. So I have that one computed as well. So this one is what's known as a partial R. At this point, there's only one variable in the model, so you can just think of it as R. By the way, the difference between these two is coming in unit 4. We're going to add that piece later on. So effect sizes can be generated directly from the t-test statistics. Adding this argument to the function does the math for you. Do you want to see the next one? Are we feeling okay with this? Okay. All right. The second question was write syntax to predict science from school type, in which in the original variable, 1 is public and 2 is private. But I wanted you to make it so that private was the reference. So first thing, I have to recode the variable into a new version in which private is 0. And if it's public, and private is, hang on, private is the restaurant. Yes. I have it backwards. I want public to be the reference. That's what I want. I'm doing my own thing, but this actually works well as a pedagogical exercise. So I made a new variable called private. That's empty. And then if school type were 2, meaning it's private, then it gets to be a 0. So it's actually my comment that it's. See, I'm fixing it for future me. And if school type were 1 originally, then it's going to be 1. So first step, I need to run this and make sure it worked. I can do that by checking that I have a new column at the end of my data set that has 0s and 1s instead. I can look at that new column by double-clicking on that object and seeing that it's on the end here. So most of the folks here are in public school. Very few, not readily seeable. There they are. There's some ones at the bottom that have that as well. There we go. Don't need the functions open at the moment. We'll get rid of that. So then in the call, I'm using science as the outcome and private is my new predictor. And I'm asking for effect sizes on that one as well. So where's my residual variance? What number is it? We'll act like this was a homework problem. Yes, the 93, very good. So this is the amount of variability that remains in science scores after accounting for whether you go to public school or private school. Where's the variability that we started with? I can't read lips very well, but that sounded right to me. You can talk or you can type. You can talk or you can type. Equal opportunity. Where's the original variability in this outcome? Yeah, it's the 94. So I'm just going to ask you to eyeball this. Do you think going from 94 to 93 is a big deal? Not really. So just on the surface, it's like, well, public versus private doesn't appear to matter too much, but we'll go through the rest of this anyway. So the intercept down here, the answer for the "you are here" sign of science is specific to what 0 means on this variable. So 0 means that they are in public school based on how I coded it. Isn't it? Hang on. Nope. I'm confusing myself. School type is 2 is private. Yep. So they are in private school. For that group, here we go. They get a 53.8 on their expected science. Slope means that whoever the one group is lower by 2. So I saw a few folks had this backwards on homework. The slope always talks about what happens to the one group relative to the 0 group. What would happen if we changed it? Let's make
It will
a new
become
version. Go ahead.
it will become positive.
Yep. So I'm just going to switch the 1 and the 2 here as to who is whom, and rerun. Did I switch it? Yeah. You're right. I'll have to figure out why it's not working offline, but it switches it around. So that's why the wording has to be how the one group differs from the 0 group. And this is a really important lesson as to why comments are helpful. Because you can see I'm trying to figure this out on the fly while I'm talking and failing. So future you, take note. It can be difficult to make sure that your coding is correct. But one thing that you can do is to generate means for each group, for instance. And then you can see, well, which way do the means go? The slope should match that direction. So once you are all the way done with your analysis and you're happy with how things turned out, that's the point at which you would turn on the text start command. Run all of your analyses again, because then it will send it to that external file, and then run this to close it. And then you don't have to have R open to answer questions in your homework. You can just have the output that you've generated, if that's more convenient for you. Okay, questions? Folks who fought with R over the weekend. What am I forgetting to tell you about? I haven't forgotten anything? Okay.
I had a question from the homework.
Yeah.
It wasn't necessarily, well, it could have been that I was doing something wrong in R, but like for question 15, when it said the standardized estimate, I think it was 15 and 22. Can you explain that to me?
Yeah. So let me open homework so that we have the context of the question. I have a whole bunch of pretend logins that I use here. Make sure that it goes in. Okay, let me open. Nope. It never wants to stay. There we go. So 15 was enter the standardized estimate for the intercept, and 22 is enter the standardized estimate for the slope. So that is one variation of effect size that is commonly used in regression. I wanted to show it to you, and indeed the command that generates those numbers is up here, LM beta. So for instance, if I have, in this example, I was predicting math from centered writing. So I will rerun that output so that we have it. So this is the fixed intercept for math in the original solution. This is the fixed slope for writing predicting math in the original solution. Both of those have units attached to them. You can take the object that your results are stored under. So I saved that analysis as math underscore write 50 with the LM beta command. And if I just run that little thing, I get this much. So what it is doing essentially under the hood is taking this predictor and the outcome and changing it over into a z-score. Do you remember z-scores from intro? Maybe? The mean of a z-score is 0, the standard deviation is 1. So it puts it on an equal footing, so to speak. And then it essentially reruns the analysis on those z-scored variables. So the answer for the standardized coefficient for the intercept is returned as NA, which is actually 0. In a standardized solution, the intercept will always be 0 because the job of an intercept normally is to adjust for any mean differences in the scale of x and y. There won't be any mean differences in z-score land, so we don't have to adjust. The standardized slope then, which is the answer to number 22, is right here. It would be 0.63 in this example. So what that means is that for every standard deviation increase in x, that's what a unit is, then the y goes up in 0.6327 standardized units as well. And this is the same thing as a Pearson correlation between these two variables in this instance in which there's only one predictor for this outcome. So this is a separate command to generate a different kind of effect size. I don't have that included in my function, but I have this this package. It's LM beta, I think, is the name of the package actually too. Yep. I found that does that neatly. Okay, does that help for that one? Yes, cool. What else am I forgetting? Not forgetting anything? Rumors? Y'all are quiet today. Good. It's like, wait, I'm on Zoom too. What do I call myself? Zoomers, maybe, something like that. Okay. Are there any other pieces of homework that you want to go over? Because everybody got it done. I can. That's so exciting. That like never happens. Well, I did look at what common sources of mistakes were, and that actually feeds into a question that folks had on review. I think in Excel, I think in spreadsheets, by the way, so I make these things periodically. Whatever I do in class in a spreadsheet, though, I will post after class, so you don't have to try and copy it down. But I had a few questions about terminology. There are several terms that sound like synonyms, but they aren't. Standard deviation, error, variance, or residual variance. Same concept. Of these three, which square does standard deviation go? So the question is, are we talking about dispersion across the people in your sample of your outcome? Why do some people have higher outcomes than others? I don't know. Or are we talking about dispersion of the results across repeated samples of the same kind? Two different flavors of dispersion. So if I want to talk about standard deviation or the residual kind, I'll just stick that in the front, meaning leftover. This one to match. Where does this go? Which of these four? Is it squared or unsquared? We got a guess for C2, B2. It's multiple choice. So. Okay, we got B2, unsquared, B2. It's definitely unsquared. I'll give you that one. Are we talking about the variability within a sample or across samples? That's the question. Within, yeah. This goes here. So when you're just describing data, like you run descriptives on a data set and you get mean and variance and standard deviation, that is referring to how different the people's outcomes are within your sample. And standard deviation is how different, on average, any one person's outcome is from the mean of the sample. In the context of the model, it means the same thing. However, it's talking about the e's specifically, not the y. So how discrepant are the e's relative to a mean of 0? So R actually does you no favors in this. The original LM output mixes together standard deviation and standard error. But this is not something we typically pay attention to. What is the squared version of this? Yeah, this one goes here. So like in the R output, when I say what's the residual variance and it's 93 or something, that's the squared version. Variance is squared so that the positive and negative deviations don't cancel out. But if you want to talk about an average deviation of any person relative to what the model says their outcome should be, average deviation is unsquared. You rarely will see this. It's this one is what we pay attention to. I'm going to bold it for that reason. Now, standard error. So you can have a standard error for any sample statistic. It can be the standard error for a mean, for an intercept, for a slope, anything you can compute from data, you can compute an expected inconsistency of it. But inconsistency across what? People or samples? Where does this one go? People, 1 vote for samples. Gonna need a tiebreaker. Yeah, this one goes to samples. So we're not talking about people anymore for standard errors. We're talking about the results from the people and how wiggly those expected results would be across repeated samples. What goes into standard error? There's 2 main things. I don't need to have the formula memorized, just the concept of what contributes to it. If you want your results to be less wiggly, what do? You're designing a research study.
Have more people.
Have more people, yes. So in the formula for standard error, people, the number of people, minus the number of fixed effects as degrees of freedom, that's on the bottom. So more people means your standard error is smaller. What's on the top? Mean minus HO, that is T instead. Let me pull up where I'm looking for. We'll review that as well. So I'm in slide 33 of lecture 2. The standard error for a slope has the residual variance for the model on top. And we just said that that has to do with the people. So the more spread out the people in your sample are, the more wiggly your results are going to be. So these things are yoked together in that residual variance contributes to standard error along with sample size. But standard error is a samples thing, whereas variance is a people thing. Now, what's this one? It's empty. What's squared samples analog? What do we call that? I said this once very briefly, so I'll be really impressed if you remember. That's actually residual variance. Yeah. Yeah, this is something that you will only see in quantitative simulation research for the most part. We call it sampling variance. And I don't want to do that to you. It's too close to this one. But that's what people would call it. So the standard error squared is your sampling. It's the variance of that across samples. So in practice, copy this down so we have a new version. We pay attention to these two. Variance across the people, average discrepancy from the population is the standard error for the results. And yes, it's confusing because they're at different levels of abstraction. Variance is talking about the people in a sample. Standard error is talking about the behavior across samples of your results. Variance is squared. Standard error is unsquared. In that topic on your request for review, is that helpful? Or are there follow-ups? Okay. One helpful. So these are the two that we keep track of for the most part. The other thing, the reason I got this out, let's talk about T. By the way, this is Excel being mad at me because all of these formulas want something to be in these cells. We'll put something in there in just a minute. So I wanted to just walk through sort of the logic of hypothesis testing and how the pieces fit together one more time, because I know that it's a lot to hang on to. So I've pasted in this picture from one of the slides to help guide us. So let's say that in this hypothetical example, our null hypothesis for what is expected is 0. So that's standard practice we'll do here. let's say that I have a slope of 6. Is 6 good? Is 6 a lot? Well, it depends on the units. Are we in like pounds, inches, scores, answers, what have you, dollars? Well, one of the things that can help is if I knew that the slope standard error was 2. Well, that changes things because now we have 6 minus 0 divided by 2 is 3. So I have to put a formula in here to link those pieces together. What you got as the estimate minus what you expected as the null divided by the expected wiggliness of that slope. So t in this case is 3. Let's say that I have a sample of 10 people. It's a pilot study. I'm a grad student. I don't have any money. That's the best I could do. What are my degrees of freedom? Sample size minus the number of fixed effects. If I have 10 people, what goes in this cell? How many fixed effects would I have in order to get at least one slope? I have one for the slope, but if I have a slope, I have to have something else with it. It's implicit because it's not on the spreadsheet. But what's in an empty model? The intercept. The intercept is always there. So it's 2, exactly. We had to have an intercept because we start off with the best guess that everybody gets the mean, and then we refine that guess based on the predictor variable the slope is for. So there's 2 things being estimated. So if I have 10 people in my sample and 2 fixed effects, that creates denominator degrees of freedom of 8. So let me paste that down through all the cells in this scenario here. This one auto-populated. For people who like code, thank you. So this has t distributions built into it as a function in Excel and as a function in R and every other package. So this is telling you, given 8 degrees of freedom, so that's the only thing that's going into this function, not what happened, but just setting up where the goalposts are. For 8 people, my t needs to be past 2.3. That's where the goalposts are. Now, why does that make sense? If we think about what the units are in these things, a slope is the change in y for a 1 unit change in x, right? So that's, we'll go y over x as an idea of that. The slope standard error, which we just looked at, but let me put that back up here. Nope, come back. There we go. Y variance, and on the bottom is x variance. So it's the same idea of y over x. So when we take a slope that's y over x in units and divide it by a standard error that's also y over x, that's like flipping it upside down and the units cancel. So t is not in units of y or x, it's standardized. So 2.3 means that a slope of 6 is 2.3 standard errors away from the null hypothesis. So if we go down here on our plot, we would be over on this side, meaning we're past the goalpost on the right side. We would declare the result significant at an alpha level of 0.05. Now, what if the standard error were 3? Yeah, note what changes. Same slope, but now we expect more inconsistency about it. There's a stronger noise, but the same signal. Now t is only 2. 2 doesn't meet the cutoff. More specifically, we would observe a slope this extreme or more, like 8% of the time. That's what a p-value of 0.08 means, which is more than our cutoff of 0.05. So if we were in this first situation, we would say that this slope is significantly positive. What would I call this one? If I'm using an alpha of 0.05. It's still positive though, right?
That's non-significant though.
Yep, I'd say non-significantly positive. And people may yell at you for that, but I'm not one of them. I think direction matters. Particularly if you're talking about a pilot study of 10 people, where you're not going to find significance most of the time anyway. Now, what about down here? Now the slope is negative. Same goalposts. Now we're just talking about the negative side. Same p-value. So this one would be significantly negative, and this one would be non-significantly negative. Okay, with me so far? Now, what if reviewer 2 comes back and says, I don't like an alpha of 0.05. This is bad. Alpha inflation. Researcher degrees of freedom. Bad. I want you to use 0.01 instead. Okay, well, now, based on the same input of degrees of freedom, I've moved the goalposts. The point where 1% starts is here. So if I want an alpha of 0.01, what's my new label? Do we still say significantly positive if we're using an alpha of 0.01? Yeah, we changed the goalposts. It's the same data, it's the same relationship. But now we have changed what we're calling unexpected. Unexpected happens less than 1% of the time if you have an alpha of 0.01. Unexpected happens less than 5% of the time if you have an alpha of 0.05, where the area under this curve is the amount of unexpected. So all of these would be non-significant at an alpha of 0.01. Now, we can't control residual variance. We can't control how different people are from each other in most cases, but we can control sample size. Do you think a study of 10 people is a good idea? How many people do we need to do our research? More. The answer is more. So how much is more in your world? At least 20? Yeah, I'd agree with that. What if we had like 500 people? That's pretty good. If I had 500 people, what's my degrees of freedom? $498. Yep. Now watch what happens to the goalposts. They're moved in. It is easier to have a significant result if you have more people. So now, regardless of like this result, regardless of whether you want to use 05 or 01, that's significant either way. So you don't have these two things under your control. You don't have the slope under your control, and you don't have the part of the standard error that relates to y. You potentially have sample size under your control. And I will finish out the table and post this for when we finish up this afternoon, this evening, actually.
I have
All
a
right,
question.
Yeah, please do.
So earlier when you were saying that the alpha, when the alpha was 0.05 and we had the 2.306, so we compared that to the t statistic, which was 3,
Yep.
and that is when we said, okay, like how do those two things determine the p-value, I guess, or determine our conclusion? How do those things work together?
Okay.
Because the only reason I'm asking, because when the alpha was 0.01 and then it was 3.355, And I saw that T was equal to 2, I was thinking, okay, maybe it is significant. But I get that the p-value was under or was more than a 0.01. So I'm just wondering, do you get what my question is?
I think I do. I think I do. So
Okay.
T is what happened to you, right? Like that is the result you got from your data. The question is, how do you interpret it and whether you like trust it? And so these aspects right here, this is setting up the field. So these are where the goalposts are.
Right.
So if you are okay with being wrong 5% of the time, this is the goalpost that would be warranted by the sample size. And the more people you get, like if I put a 50 here, it moves the goalpost in. Makes it easier to get out. T is where you are on this field. So if I have a T of 3, I'm out here.
Right.
And I'm out
But
here.
if I'm at 0.01 for alpha and I have a T of 2, oh, I'm in. Okay.
Yeah, so like if we just look at, let's just isolate this row right here so we can focus on the question. So T is what happened to you. So like T is here, like this is where 3 is, regardless of anything else. The question is it on the right or the left side of the boundary of where significance is based on how unexpected you're willing to say is unexpected? So where the goalposts are is something you're supposed to decide ahead of time by saying, do you want, what's your alpha? Do you want to be wrong either way or only one way? That's one-tailed versus two-tailed. And then T versus Z, where it's always going to be T. So like in practice, all of these steps of logic get reduced to this number, which way does the slope go, and what is the p-value? So if I see a p-value of 0.017, that corresponds to the amount of area under this curve that you would expect going further out this way or that way. The question is that enough to be declared unexpected? And that's based on where your goalposts are. So T is what happened. The critical value is like just setting up the field of play for anybody's research to play on. Like these are the boundaries given your sample size that T has to cross to be declared non-significant.
Got it.
So then the p-value, like that tells you at an alpha of 0.01, we would not say this is significant because it's higher than that. It's 0.017. At an alpha of 0.05, that p-value is under 0.05, so we would say it's significant. So it used to be that like when folks learned statistics, they would have to look this stuff up. Like there'd be a table like in a stats book that had all these critical values and you had to compare your result to that. That's happening like implicitly in the programs at this point. So T is something you can kind of skip over for the most part, but it is useful in generating effect sizes. So we can turn a T into a D for a standardized mean difference. We can turn it into a correlation type effect size as well. Better? Trying? Okay, other questions on this topic? Is it break time? Feels like break time. It feels like break time. Okay, 10 minutes per usual. All right, then that would be about 6:25. I will see you in a bit.